So we just have the 3 that are due Wednesday. So these are work energy problems. So that'd be the approach to be taken on them. All right, so when you're doing work energy, what you've got there is you've got the potential energy. That's the weight times the height. You got the kinetic energy, and that's 1/2 mv squared. And then you got spring energy, which is 1/2 ks squared. And S is the amount of compression or amount of stretch in the spring. So those are the 3 kinds of energy that we deal with in our mechanical systems. And then work is caused by a force from outside the system. So when you're doing this stuff, you decide on a system. And so what work is you add up the forces times the angle between the force and the displacement, which we could call theta, and then times the displacement. So that's basically what we got here. So it's just a matter, when I do these, I just set up a table and just work through it using those definitions there. All right, so the deal is you want to just figure out, how to calculate those things. So you need the weight, which usually you're given that. You need the height above a datum, so you need to determine what your datum is. Datum is a point that you measure from. Usually I put the datum at the bottom, so I put it there. So you'll need the height up there. All right, and we'll have this box come on down here. So, all right, so you need that. You need the mass, which usually you're given. You need the velocity, which you have the initial velocity here. And you need the spring constant and the current length of the spring and the unstretched length of the spring. There's no springs on this one, so that will zero out, okay? So you could find the weight times the height, and that'll be your potential energy for elevation. You can find 1/2 mv squared because you got the mass, and then you've got the velocity, so you can do that. Add those up, and you'll have your initial energy, okay? Now what you want to do here is get the weight, which comes down like that, and then find the normal force, and then find the frictional force. So the force of friction is mu Fn. Okay. So what you want to do there is find that friction. Which ought to be 4.64, okay, when you work through that. And then the work then is the friction times the distance, because the friction acts in the same way as the displacement. Okay, so that's the work. So that'll be a minus value because it's work, it's friction, it's slowing the block down, it's taking energy out of the block. Okay. And then what's going to happen here is you're going to end up with a final value right there, and you want to equate that to the kinetic energy. So what you're going to end up having here is 1/2 mv at b squared is equal to whatever it is that you get there. And then you can solve it for VB, and that comes out to be 6.08 meters per second.
Use the coefficient, use that for static friction?
No. Yeah, this one's moving, so it'd be kinetic. Yeah, it's motion, so it'd be kinetic. All right. Other questions on that one? Okay. right? And then, you know, I just set those up in tables and put everything in there. It's usually how I do those. All right, this next one, got a weight on a cable. It's pushed by the spring. It swings up to position B. We want to find that angle at position B. And you're given the uncompressed length of the spring is 0.42. You're given K, and the motion of the spring is stopped at the position shown. So we've got a little stopper here, right there. So that spring is going to, after the ball is shot out, the spring will stop there, okay? So the maximum length of the spring is 0.32 meters. That's the length of the spring when the ball swings up to B. Okay, the mass is 0.28 kilograms. You can get the weight here. That's 2.75 newtons. All right, so what you want to do on this one is a similar kind of analysis here. Now, what you're really going to solve for on this one, even though the call out there is for the angle, I think really what you want to solve for is the height at B. If you've got that, you can work your way into the angle. But you need to get that height at B. All right, so to do that, we just want to do kind of the basic setup stuff. So get a datum down there. That's probably what I would do. Now, if you want to find the spring energy at A, what you would do first would be to find the amount of compression, or S sub A, I guess we call it. All right, now that thing's 0.18 meters long, and the unstretched length is 0.42. So 0.42 minus 0.18 gets you 0.24 meters. So that's the stretch in the spring at A. Or actually the compression, I guess it would be. So if you want to find the spring energy at A, what you're going to do is take 1/2 times K. Now what K is, it's given there, it's 60 newtons per meter. And then times 0.24 meters squared. Run that and you'll get the energy there. It's 1.73. And what energy is Newton meters. So the one important thing here is to find the stretch. Don't, sometimes people, to find the compressed length of the spring. That's the difference between the unstretched length or uncompressed length, which is 0.42, and 0.18, which is the length that the spring is at A. Okay. All right. Now the thing's at datum, so there's no potential energy there, and it doesn't have any velocity, so the kinetic is 0. So if you look at the initial condition of this thing, that's the energy that you've got in the system. We're considering the system to be the spring and the weight, or the mass, whatever you want to call it. So that's 1.73 Newton meters is what we got. Okay. So what we got here at A is there's no potential energy. There's 1.73 Newton meters. There's no kinetic, so that's how much energy you've got to start with. And then you just need to figure out what happens to that energy. Okay. So now as this ball travels, there is a force exerted on it, but the force goes through the cable. Okay, so the force goes that way, and the velocity is normal to the force at all times. So that force of the cable, so F cable, is perpendicular to the velocity of the weight. So F cable doesn't do any work, okay? So that's something to remember about this stuff. So if the force is normal to the motion, it doesn't do any work, okay? So keep that in mind, okay? So there's no work going on here. There's no friction, nothing like that. And the force of that cable doesn't do any work. So that's going to be a 0 here. So you're going to have 1.73 total to work with. All right. So you got to figure out how these three things relate to the 1.73. And really what you're going to want to do is kind of back in and solve for the potential energy, which you don't know. What the potential energy is 1.43 is what it comes out to be. You can kind of go through and get that figured up, but that's what the potential energy work comes out to be. Okay. So what's going to happen here when you get that number is you're going to go ahead and, and set 1.43 equal to weight times the height, and then you can work through that and get the height. That's how this works. And so the height is 0.52 meters. Okay, that's how high the ball has gone. Even though it's swinging, it doesn't make any difference. I mean, that's the height of it, and you can find that using the work energy stuff, okay? So once you've got that, that's H, okay? Now, that's above the datum, is where it's at. So that's HB. So what you've got is you got this ball up here, and it's swung up to that height above the datum. Now, you know a few things about this. You know this length right here is 0.82. So that's going to leave, what, about 0.3 right here, I think. And then you know the length of this cable is 0.82 meters also. So I think you should be able to figure up a triangle there to figure out the angle. So you'll end up doing a bit of trigonometry there to find the angle. Okay. Yeah. The 1.43. Well, there's still a bit of spring energy in there because the spring gets stopped. The spring doesn't get to expand out to its total length that it wants to go to. It wants to go to 0.42, but it's not able to do that because there's a stopper there in the way. Okay. So there's a bit of spring energy. You have to take that away from the total to get the potential. All right, so you kind of work in through the height and the length of the cable there to figure out the angle. You got any questions on that? All right, and then the last one here, we're going to drop this collar and let it slide down that shaft. We've got it on a spring at point B. Collar starts at rest at A, then it slides down the shaft. We're given the average force of friction. We want to find the velocity at C. All right, so we got two positions here to be analyzing the thing at. So we want to figure out its velocity right there. All right. Okay, now you're going to want to find the length from B to C. And I think you got a nice triangle there to do it with, so now, it should be pretty straight up. So I always like to put datum, again, datum's the point that I measure from, down at the bottom. I don't like dealing with negative potential energy. It's not that big of a deal. You can do it, but I usually keep datum down at the bottom, so I'd set it down there. Now, as this thing moves, you're going to have that force of the spring, and you're going to have a changing force of the spring because the length of the spring changes. And also that angle changes as the thing moves. So, I really wouldn't want to mess with this doing F equals ma or something, because the force, both its magnitude and its angle, is constantly changing. So this is definitely a work energy problem. See, the fact that the angle changes doesn't affect work energy. What you're going to do on this thing is treat your system as the spring in the block. So if you do that, the energy is just a magnitude. You don't have to worry about direction on energy. So those are kind of the two things that I remember about this work energy stuff. One is that it's just a magnitude, and the other is that that if there's a force normal, it doesn't do any work. Okay. So what we're going to do on this is treat the system as being the spring in the block, the collar. And if you do that, it's pretty straight up. You're just going to find the energy at A and then find it and then kind of work through B. You've got the average friction right there, and you got the distance over which the friction's applied. So you should be able to come up with the work. All right. So, you can just kind of work on through this, and you can make sure you're getting these, but that ought to be about 3.41. This ought to be about 4.14, and this ought to be about 3.67. That's how the numbers should work out. You can get some of those other numbers in there, but that's just some of the numbers you ought to be getting. Okay, now there's no potential when you get to the other side there at C, because you're down at the datum. There is spring energy, and you want to be able to equate the total energy that's left over, 0.919, and set that equal to 0.30 v squared, and then you can solve for v, 1.75 meters per second. Okay. So that's just some of the numbers there in the table. You've got some stuff to fill in here. At those places. But that's the general outline of how to do this. I think really once you get this work energy kind of figured out, it's a pretty straightforward way of analyzing things. I mean, there isn't always all that much to it. It's just a matter of getting that table filled in. The two tricks that I know is one are things you don't have to worry about, and that's the force normal to the velocity. It doesn't do any work. And then the direction of work, and it doesn't matter either. It's just a magnitude is all it is. All right. So you got any questions on that? Okay. All right.